Welcome back to the 8th part on my simple electronic constant current load. This time I want to do a transient analysis of that thingy. And what is a transient? A transient is the opposite of a steady state. Currently, the whole thing runs in a steady state. That is, at 20 volts, 500 milliamps. And this is just the voltage drop across the shunt resistor, including the second shunt in the ammeter. So, if that is a steady state, what is a transient? A transient is simply a change from one steady state into another. Like, I'm decreasing the current to 400 milliamps or increasing the current again to 500 milliamps. That shouldn't be critical. What's more critical is like I suddenly, that switch here is in series with the power supply. If I suddenly, cut off the load, not so interesting, but suddenly put on a load. Or what happens if I switch that thing on and off? Will it still be work in a stable state? Or if I change the range suddenly, go down to my low range and up to my high range, and what's happened here? It's oscillating again. I guess that might be a long video, and you see I can simply by adjusting it a little bit down and up to 500 milliamps, I can get rid of that oscillation, but that's obviously not acceptable. I mean, if you are have that on your bench and you switch the range and it starts oscillating, not nice. So that's basically our first transient we had a look at, and it's not working so well, does it? So let's have a look at the circuit, why that is. So the culprit is clearly somewhere here in the current regulation. So let's zoom in. So our current regulation itself with the op amp, my set voltage coming in here and my feedback voltage coming here over my shunt resistor, including the 40 milliohms in the ammeter. That works perfectly fine as long as I'm slowly changing here the input voltage. We struggled a whole lot with getting that thing stable and not oscillating. Card link. But when I put a hard transient here at the input, I give that, like a pendulum, I give that a hard kick and it starts oscillating, obviously. So what we can do about that is, avoid giving it hard kicks. And the very hard kick with a lot of spike and really dirty stuff comes, of course, if I actuate the switch here, which either gives the 2.5 stabilized directly to the potentiometer, the clockwise connection of the potentiometer, or via that resistor, giving us the lower current range. A simple way to fix that would be to add another capacitor somewhere here. But let's first try to capture with the scope what's really happening. So here we are in the steady state, that was a lower current range, and then I actuated the switch, and you see what's coming out of that switch. The input through a resistor network, the input signal to our positive input of the op amp. it's a mess. It's a complete mess. And yeah, we can scroll through here, and it takes a whole lot of time until that signal is stable again. And in effect, what's happening here, especially at the beginning, yeah, we know that our feedback loop of our current regulation is prone to oscillation. And what we do here, oscillating like a pendulum, maybe I should use another color, like a pendulum, and we give that pendulum here a real hard kick. And obviously all our RC elements in the feedback loop are not enough to dampen that initial kick, so it starts oscillating. But that's quite simple to alleviate that problem. We just have to put here another capacitor. Yeah, and have here really high, I mean, this is basically very high impedance, the input, and we put that here in parallel to that resistor, which is 270K, and let me think about the value for just a second. Yeah, just some back-of-the-envelope calculations. So our timescale on the oscilloscope was 100 microseconds. There we saw the spiky stuff. Our resistor is, order of magnitude 200 kiloohms. It depends a little bit if you, take that as an RC element. In parallel RC element, that R5 has 270K. If you look at that as an RC element, that has 200K. So order of magnitude 200K. And the formula for calculating the time constant, let me zoom out again. The time constant for RC element is tau equals R times C. So the capacity we are searching for is tau over R, or 100 microseconds over 200 kiloohms. And that yields us 0.5 nanofarad capacitor. Let's be conservative and start with 1 nanofarad and see what happens. And things look much better. Here at the back we were at the steady state, and then we turned the switch. There is still some noise here on the signal, and we're still ending up in an oscillation. Okay, so next stop, 10 nanofarads. And that seems to do the trick. I mean, we're here to the left on the steady state, and then when we flip the switch, there's still some stuff here, but that's negligible until we reach our full, nice and slowly 500 milliamps. Looks nice, doesn't it? The same in real time. Let me change the time base. 1 millisecond, and I'm flipping the range switch. That's how it should work. That's the 10 nanofarad I lopped in here parallel to R5. That's here, and just after R4. Because that works so nice. Full view again. changing the range switch, yeah, 500 milliamps, 50 milliamps, or yeah, with my 5% resistors, 54, 55, whatever. Yeah, works like a charm. So let's go to 500 milliamp range again, and now try switching it off. Okay, that's easy, but switching it on. There's the oscillations again. What's happening here? Let me capture that. I connected a additional probe, the pinky one. That's our battery rail, and you see, that looks just awful. And of course, we are going into oscillations, while our positive input to our op amp is nicely behaved, but the power supply to the op amp itself, yeah, that's not good. Yeah, and the culprit in that case must be somewhere, of course, in our power supply. So let's zoom in. So we have our mandatory 100 nano capacitors, on the power supply of our op amps, and they should be good enough for any sudden power requirements from the op amps, changing their outputs and so on. But up to now we have absolutely no filtering here on our 6 volt to 9 volt rail. We just have the battery switched battery connection, and the switch makes a lot of noise when we switch it on, and our reverse voltage protection here, but nothing else. So let's put in a capacitor here, and since this is our main rail, so 6 volts to 9 volts, we put in some electrolytic stuff, something big. Not too big, mind you, but something to help us out here. So I shoved in a 100 microfarad, 16 volt electrolytic capacitor, and now our pink line, our main power rail is coming up, nice and clean. So no problems there, but the positive input of our op amp is still ramping up a little bit too steep, so our current again starts oscillating. So let's go up with that capacitor here, which is smoothing out the positive input from we're currently at what was it, 10 nanofarads, 10 nano, to let's say 100 nano, and let's try the whole stuff again. So our battery rail is now ramping up without any bouncing from the switch, no problem. And our positive input to the op amp is ramping up much more slowly due to the 10 times bigger capacitor at it, 100 nano instead of 10 nano. And our current is also ramping up nicely to the 500 milliamps. Did I capture this in its entirety? Not quite. Doesn't matter, but it doesn't oscillate. I think for that simple circuit, we can ignore that little fluttering here. We could make up the we could slow down the ramp up even more, But instead I want to see what happens, yeah, if a 47 nanofarad capacitor would be enough. So let's try that. Yeah, works with 47 nanos as well. We still have that little here, but yeah, it's okay. And because it's so nice, let's try it again. Yeah, works like a charm. Anyway, let's review what we've done so far. Actually, not that much. We added here at the positive input another capacitor, and yeah, we are now at 47 nanofarads. 10 nanofarads was enough to filter out the effects, yeah, the bouncing of the switch here, which would have, yeah, kicked our current regulation circuit. Yeah, you remember the pendulum, and we kick it and it starts swinging. Then we added a 100 microfarad capacitor here to, yeah, alleviate the bouncing from the power switch, which, yeah, of course, sent some very bad voltage spikes through the whole thing and also got it swinging. And we reduced that yeah, and we went up to 100 nanofarads in conjunction with that, because yeah, our power rail was now ramping up really nice, but yeah, still some oscillations here, and we went back down to 47 nanofarads. That is obviously enough, yeah, to filter that input, to keep that stable, yeah, protected from any spikes which mess up our current regulation. So, last but probably not least, what happens if I suddenly put a load on the thing? And that's what that switch is for. I mentioned it in series with my power supply, so I can, yeah, break the connection. Yeah, current voltage goes down to 0, and I can make the connection, and we have current oscillation again. That's not too nice. If I go down with the current a little bit, it should, yeah, it stabilizes itself, and I can go back to 500 milliamps. But if I break the circuit and establish it again, yeah, we are oscillating. Why? And the problem lies with our current regulation, of course, and how it works. I mean, we put in here a set voltage, and I don't know, at 500 milliamps. Do I have that here? Yeah, about 0.27 volts. So we are here at 0.2. No, that's wrong. Sorry. 500. Yeah, 0.27 volts. It's correct. At this point. Okay. We have nothing connected here. So whatever that MOSFET does doesn't matter. We have 0 volts here. Yeah, this is going to ground. And yeah, you see the problem. As long as no load is connected here, and we have our set voltage for specific current, yeah, the whole thing here, the op amp drives it output high, because yeah, it wants its negative input, yeah, to be as high as its positive input. So it goes really, it drives its output to the maximum it can drive it to, and yeah, that's unfortunately our power rail. So 6 volts to 9 volts here in that state. So the MOSFET is driven, when no load is connected, completely open, yeah, to the max. And then we suddenly connect the load. Bang. And yeah, then with yeah, also bouncing off the key of the switch, yeah, my external switch in series to the power supply, yeah, you see the problem. We get a lot of whole spiky stuff around here, and plunging in here, and yeah, again, pendulum, big kick, and it oscillates. And we have there are two alternatives to mitigate that problem. Either we do our dampening here inside our feedback loop, yeah, we increase that dampening further, or we try to avoid those really, really high spikes here. Let me think about that. The resolution was actually quite simple, and it worked the the first time in the first iteration, which is a first for this project. Yeah, I'll show you in a second, but yeah, you see here that violent bouncing of that big switch, and but yeah, within yeah, after the bouncing stops within a millisecond, yeah, the current is stable, which is, yeah, which is what you want. And you also see that the oscillation, yeah, the pendulum getting a big hit, how that is dampened now very nicely. And yeah, I show you the what I changed. So I thought about a lot of possibilities to yeah, to dampen basically that big, yeah, transient as soon yeah, our MOSFET, remember, is completely open, and suddenly current shoots through here, and we have a big voltage drop here, and yeah, you could make a really big capacitor around here, which would yeah, otherwise influence the behavior of that circuit for low currents very negatively. So instead I went with the existing RC networks here in our feedback loop, and just yeah, on the first try I increased the value of that capacitor from 10 to 47 nanofarads. Makes the whole sorry, feedback loop even more slow, but yeah, I mean, it's good enough. Good enough. I'm happy for now. So yeah, everything seems to work now. We have all our 3 transients under control. So hard load switch. Okay. That's working now fine. Range switch works fine as well. And of course, switching the whole thing on and off. Yeah, very nice. And now I will take another, it will take another few weeks, I guess, at least until I made a layout for a PCB that will fit into that case here, hopefully fit. And yeah, I have to order some parts, and I need at least $50 to order a digit key, so I won't have to pay the shipping costs to Germany, which are enormous. And yeah, then we'll continue with that. And meanwhile, there are some other things I'll have to do, and I will show you. Until then, bye.